This is lecture outline 8, Roman numeral 3. In the first two Roman numerals, we talked about the wave-like and particle-like properties of light or electromagnetic radiation. Today we're going to talk about, or in this video, we're going to talk about atomic spectra and the Bohr atom, and we're really going to start talking about the wave-like and particle-like properties of an electron. And really, we're going to focus on the wave-like properties of an electron because the particle-like property that it has mass, that mass can have a position as well, that is pretty well known. The wave-like properties are the more hard to get at piece, and we're going to talk a lot about them. But along the way, we're going to figure out where the electrons are in atoms. And so let's talk about atomic spectra and the Bohr atom. And where we're going to start is that sunlight is white light, and we're going to work our way towards the Bohr atom. So white light, it contains a continuous spectrum of all visible colors, some infrared and some ultraviolet, and there's a nice picture of it in color. And you can see one thing to note is that the red here is at the top. The violet is down here at the bottom, so ultraviolet, which we can't see, would be down here as well. And so a couple notes we want to make about this. Up here is the red, down here is the violet, and the prism separates those colors. So that's white light coming in, the prism separates it, refracts it into its colors, and as a side note, violet light is refracted more. Now, what we're going to do is we're going to look at the results of flame tests for aqueous metal ions. And the thing that we have to know about this is, first off, these are metal ions. They're put into a flame, and that each of these metal ions have different colors when they're put into a flame. And so yellow for sodium, purple, red, and barium is sort of a whitish yellow. So first off we have sodium, potassium, lithium. We have red, yellow, purple, red, and sort of whitish yellow. And let's talk a little bit about this process here. So the aqueous ions, when they're put into a flame, these metal ions, if you will, so the flame adds a large amount of energy to the metals. Which makes the metals emit light. And true, that is a simplification of the process. If you have questions, we can talk about the process in more detail in office hours or any of the times that you'll be seeing me online. But that's a simple process. Give atoms energy. One way to do it is a flame. Those atoms then emit light. And this is for metals. If we do the same thing for gases, we observe a similar phenomenon. So they emit light as well. Now, just to tell you, this is a gas discharge tube. We would get to work with these in lab if we had this lab. But let me sketch this process for you. This gas discharge tube is in a setup. And this is showing some sort of battery or power supply. It's a power supply. It does plug in. And when you do this, you're applying approximately 5,000 volts. And approximately 0.1 amps, and basically you are adding a large amount of energy to the atoms. These atoms happen to be hydrogen atoms. So my note over here is add a large amount of energy to gas atoms, which makes the atoms emit light. So now we've got it for metals, now we've got it for gases, although mercury is a gas metal as well. So, and these are just the two easiest experiments to do. Other experiments can show that this is a general phenomenon for all elements. Here we have hydrogen in bonds, and yet we are going to focus on the fact that the hydrogen atoms in those bonds are the ones emitting light through these processes. But it is a general phenomenon. Now we're going to focus specifically on hydrogen, and when we do that, we're going to take a gas discharge tube and give it energy. Then that gas discharge tube, the hydrogen will emit light. We will pass it through a slit to get a thin beam. We will pass it through so slit creates thin beam. Then the prism refracts each color differently. And that's because of each color's different wavelength and how it interacts with the prism. Happy to say more about that in office hours too, but that's enough for now, I think. Refracts each color differently, thereby separating the colors onto some sort of screen or photographic film. And what we can see here, and again, we'll go to the actual color version. We can see that there are 1, 2, 3, 4, only 4 colors that are being emitted by the hydrogen atom. Hydrogen atoms. So 1, 2, 3. Only 4 colors being emitted by the hydrogen atoms. And that gets a couple exclamation points because at the time the scientists were stunned. They did this experiment with the full expectation that they were going to get a full rainbow of colors over here. And this is, of course, pre-quantum mechanics. This is part of the cause of why quantum mechanics was developed, or one of the initial pieces of data. One of the pieces of data. I don't know if it was initial or not. I think it was. Anyway, so now hydrogen has 4 colors, and only 4 colors. These are the only 4 colors in the visible region, at least. And this is a nice, simple experiment to show how those colors are separated. Well, if you do it for other gases, again using gas discharge tubes, we could also do this for metals as well. You would see that we get different colors. So we get different colors, yet none of them has a total spectrum of all the colors. So analyzing other gases, each gas emits a specific set of wavelengths. And one thing you'll note, and this is a general trend, although it's not the direct correlation, I will point out that as you get larger and larger atoms, really we're talking about the hydrogen atom here and the oxygen atom, you do get more wavelengths too. Good. All right, now we do this experiment in the opposite way. Instead of emitting light, we put light into the atoms. We use a diffraction grating, and again, we'll briefly show the color picture here. Take a light source, with all the colors. You go ahead and use the diffraction grating this time instead of a prism. Still separates the colors. An aperture to make a thin slit, so you can select one of the colors through a sample to a detector. So we start with all wavelengths. We use the diffraction grating to separate colors. We use an aperture to select get a thin beam, which selects a narrow range of wavelengths. Put it through the sample. The sample for hydrogen, which would be tough to do in an aqueous sample, but let's imagine. Sample for hydrogen would only absorb those same 4 colors. Still amazed by that fact. Been doing this for 20 years. Still so cool. And it's a simple experiment. Now these are the absorption and emission spectra for hydrogen. This really does look much better. In color, you can very clearly see, well, 1, 2, 3, 4 colors being, the top one is the absorption spectrum, so those are the only colors missing. The bottom one is the emission spectrum. Those are the only 4 colors present. So there's something very special about those 4 wavelengths in the visible region for hydrogen. Okay, and that's what led, among other things, to the Bohr model of the atom. The Bohr model of the atom got many things correct and in the right direction. Those are the only parts I'm going to be presenting. You do not have to know Bohr's name. You do have to know the parts of his model that are correct, and that's what I'm presenting here. So Bohr's major idea was that the energy states of the atom were quantized. Hence the name quantum mechanics. And that the amount of energy in the atom was related to the electron's position in the atom. And so a few words about quantized and what it means. Quantized means that, in this case for the energy, that the energy of the atom can only have specific values. Not any value. And as a bit of an analogy, not a perfect one, but hopefully this makes the point. If you think about going up and down a set of stairs, your height can more or less only have specific values as your foot or feet land on each step. It's very difficult for, say, for your feet or your body, your feet to have an in-between level. And the difference being, and why this is not a perfect analogy, is that for the electron, for the atom, it's impossible for it to have these in-between heights or these in-between energy values. Okay. Now, other part of this, of the Bohr model, the electrons travel in orbits that are at a fixed distance from the nucleus, and orbits that are farther away from the nucleus have higher energies. And this takes us back to something we've talked about before. If we think specifically about the hydrogen atom, then the hydrogen atom has one proton, one electron. We can think of this as a positive and a negative charge. And we've talked before about which would be a higher energy state, a positive and a negative charge with this distance, or a positive and a negative charge with a larger distance. And we decided that's similar to an analogy where a pen, if it is higher, has higher potential energy as it falls, or higher potential energy as it could fall, that a negative and a positive farther apart has a higher energy. And so that's a pretty good analogy, I think, for why an electron farther away from the nucleus would have a higher energy. 3, electrons emit radiation when they jump from an orbit with higher energy down to an orbit with lower energy. So this emission of light is going to be due to the transition of the electron from a position farther away from the nucleus to a position closer to the nucleus. And so that emitted light is telling us about the transitions of the atom, and really about the transitions of the electron or an electron in an atom as it moves from a higher to a lower energy level. When that light is absorbed, it is an electron moving from a lower to a higher energy level. So, right. That's what we're going to see. And that's the Bohr model of the atom is going to lead us to being able to calculate and understand that these wavelengths of light and the energy stored in them are moving electrons either farther away from the nucleus when that energy is absorbed, or the electrons moving closer to the nucleus when that wavelength is emitted. And so here we get to a picture of the Bohr model of the atom, and so here's the nucleus in the center, drawn much bigger than it actually is, and we have n equals 1, 2, 3, 4, and 5. I should say that there are more values of n, that these are all that fit on this slide, and that it has been shown that, and we will be able to show, that the energies of the 4 colors, 3 of which are shown here, correspond to an electron jumping, well, for 657 nanometers, that's going to be the lowest energy, longest wavelength, corresponds to an electron jumping from n equals 3 to n equals 2, as we will see. Bigger jumps will be higher energy and shorter wavelength. And then there's another one over here at 411 nanometers, and that one is from n equals 6. So electron to n equals 2. Now, each of these jumps, if we go from 3 to 1, or any of these down to 1, will be larger energy than the visible region. It'll be in the ultraviolet area. So there are other jumps. These are just the ones we can see in the visible region. Okay, now for the hydrogen atom, the Rydberg equation relates wavelength to the n values that I just showed you for the Bohr atom. The Rydberg equation looks like this: 1 over wavelength of the light being absorbed equals 1.097 times 10 to the 7th meters to the minus 1. 1 over nf squared minus 1 over ni squared. And a couple things about this. First off, when Rydberg historically developed this, it was n equals 2 and n equals 1 here, so I am altering this equation a little bit to make it more in line with my class. where the final and the initial state, we always go from final to initial, or final minus initial. So this part is specific to my class, and to keep it more in line with the material in my class. And I also add a minus sign here. That minus sign is going to be in line with what we talked about energy. When an atom emits light, then it is going to emit a wavelength, and we will get a negative wavelength here, which is a little weird. What it means is that wavelength is emitted. Again, this is also specific to my class, but I think hopefully you'll find it keeps everything more similar to the rest of my class, if that's even a word or a phrase. So for my class. So you'll see slightly different versions of the Rydberg equation when you do it in other classes, say. And so the negative sign on wavelength can mean that the light is being emitted. And then the question is, what is the wavelength of light emitted as an electron jumps from n equals 4 to n equals 1? Now, from 4 to 1 means it is getting closer to the nucleus. It is going from 4 to 1. So that means light will be emitted, and we will get, but what it means is that 1 is our final state. 4 is our initial state. Getting our calculator out here. There we go. So we'll do this first part first. I'll show you how I type it into my calculator. So it's going to be 1 squared, hit the squared button, and then I have to shift to get 1 over. Still 1, I know. Minus 4 squared, 1 over. So I get this portion is 0.9375. Multiply that times the term here. I get this large number here. And I'm going to put in scientific notation, 1, 2, 3, 4, 5, 6, 7, 1.03 times 10 to the plus 7th meters to the minus 1. Then I'm going to take the reciprocal of this number in order to get wavelength. Go back to 1.03 times 10 to the 7, then shift 1 over. I get that my wavelength is 9.71 times 10 to the minus 8. Now my meters is now, meters to the minus 1 is now meters. And since 10 to the minus 9 would be nanometers, this is equal to 97.1 nanometers. That is not in the visible region, that is in the ultraviolet region, as we expected from the previous one. So we expected that shift to be higher energy than the ones in the visible region on the previous page, and it is. Okay. This is going to be a companion problem. Oh, sorry, I have to derive another equation for you first. It says, from wavelength in the Rydberg equation, the energy of an electron in a hydrogen atom can be calculated. So in a previous lecture outline, we derived an equation, or we put together an equation where energy equals Planck's constant times the speed of light over wavelength. We now have the Rydberg equation, which is in terms of 1 over wavelength. So we will now be able to say, instead of wavelength in the denominator, let's plug in here. We still keep our h times c. So we get a new equation. This number, this constant times the speed of light, which is constant, times the Planck's constant, gives us, if we multiply all those three numbers out, we get minus 2.18 times 10 to the minus 18. Our units, which we will not show, but believe me, it works out, will be joules. Leave a little space here because we're about to put something in a minute. Remember, so far we're doing this only for hydrogen, but we want to generalize it. 1 over n final squared minus 1 over n initial squared. Okay, so this is the equation for hydrogen. Now we're going to go ahead and make it general. That is a z, and it is squared. And so this with the z equation, it's one of my favorite equations actually, and yes, that's a hint, is able to calculate the energy for the transition of an electron from a final n value from an initial to a final n value for any one electron system. Now, let me tell you what Z is. Z is the atomic number, which is the number of protons. And for hydrogen, Z equals 1, and 1 squared dropped out. And so when we go to other elements though, so let's go to helium, Z equals 2, and the one electron system, since a helium atom has 2 electrons, this equation works for the helium plus 1 ion. We can also, Z equals 3 for lithium. Lithium 2 plus has 1 electron. So hopefully you're starting to get the idea that for any one electron system, and that one electron system, by the way, is something that has just a nucleus and 1 electron, relatively simple to calculate the charge between these. Anything else with 2 or more electrons gets much more complicated. And now that we're doing it for 1 electron system, so the nucleus could be plus 1, the nucleus could be plus 2, nucleus could be plus 3, but it's still calculating the energy between 2 things, and that we can do. And I'm happy to explain more about that in office hours as to why that is, that it's only 2 particles, but for now, it works very well. Now let's use the equation we just derived to discuss something that I like to call a ladder diagram of energy levels. And we're going to be looking at the ladder energy for n equals 1, 3, and infinity, and we'll talk about what these mean, in kilojoules per mole. And because there are no absolute values in energy, we will define 0 energy state as when n equals infinity. And there's one other detail, so we have to say which 1 electron system we're using for this. And the 1 electron system we're going to use is a hydrogen atom. So this is for a hydrogen atom. And and what we'll see, and let me just sketch the idea of a ladder diagram. So if we draw a line with an arrow pointing up, and we think about energy as increasing as we go up the page, then what we should see is that, first off, we'll define n equals infinity as 1 rung on our ladder, and that will be 0 kilojoules per mole. That's what the 0 energy state is. And what we will see is that as the electron goes closer to the nucleus, all the way down, and we can continue this arrow down a little bit more to n equals 1, n equals 1 is the lowest energy state possible for an electron in the hydrogen atom, and in any atom, by the way. And that's going to be the one closest to the nucleus. And from there, though, there's going to be intermediate energy states when the electron is in n equals 3 that we're going to solve for in this problem. But according to the equations and according to quantum mechanics, n can have any value. So 2, 3, 4, 5, and as n increases, just like the Bohr model would say, the energy increases and you get farther from the nucleus as well. So let's see what this looks like now. So from previous page, we have this equation. E equals minus 2.18 times 10 to the minus 18. Those are joules times z squared times 1 minus nf squared. Sorry, 1 over nf squared minus 1 over ni squared. And what we're going to do is we're going to define, at least for our calculations, that ni will always equal infinity. And that means that we're always thinking of our electron from starting in a state that's n equals infinity. And let's talk about that. When n equals infinity, if this is the nucleus of the atom, this is the tip of my finger, and the tip of the pen is the electron and its average distance from the nucleus, then n equals 1 is here. As we move farther away, we get to n equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And n equals infinity is when the electron has left the atom. And we're not saying where it's going. All we're saying is it is no longer associated with the atom. And functionally speaking, it is at a no longer interacting with the nucleus in any way. So ni equals infinity. That's going to be our starting point. What does that mean? When n equals infinity, it means that the electron has left the atom. So n equals infinity, and let me change back to, there we go. N equals infinity means that the electron has left the atom. Is no longer interacting with the atom, that is. Okay, so that will, as we have now this term where it's 1 over infinity squared, well, 1 over infinity is 0, 1 over infinity squared is also 0. And that means that if we start here and we think about the energy going down, we can eliminate this second term, and we're left with E equals minus 2.18 times 10 to the minus 18 joules. Z equals 1 for hydrogen. Z equals 1 for hydrogen. So this just becomes 1 squared. And then we're left with 1 over n final squared. And again, this is one number, but it's always indicating that we're starting at n equals infinity and thinking of the energy change as the electron moves closer to the nucleus. And so let's do n final equals 1. For that, it's going to be 1 over 1 squared, which is still just 1, times 1, times minus 2.18 times 10 to the minus 18 joules. So the energy is just minus 2.18 times 10 to the minus 18 joules. That is our energy. And like similar calculations we've done before, this is the energy of one electron moving from n equals infinity to n equals 1. So energy of one electron moving from n equals infinity to n equals 1 in hydrogen. And I'm leaving this space down here open because I'm going to write some stuff. We're moving from, let's call it ni equals infinity to nf equals 1. Okay. And because it's the energy of one electron, we can do per electron similarly to what we've done for per photon before. And in fact, when this electron moves closer to the nucleus and gives off this energy is negative, which means this energy is given off. This is an exothermic process. Typically, the atom and the movement of the electron in the atom gives off energy in the form of light. And so you'll also see joules per photon because the photon will be given off as this process occurs. We'll talk more about that. Okay, so now we have joules per electron moved in the atom. Now we need kilojoules per mole. So let's do this process. So we have joules per electron, and minus 2.18. We'll expand it to be joules per one electron. That's the same thing, but longer line. And now we will change joules to kilojoules, 1,000 joules is 1 kilojoule, and 6.022 times 10 to the 23rd electrons is 1 mole of electrons. And if we multiply this out, so 2.18 minus exponent 18 minus divided by 1,000 times 6.022 times 10 to the 23rd. I get minus 1,313 kilojoules per mole. And that is the energy in going from 0 here at n equals infinity, or 0 energy down. So I'll draw an arrow going down. The energy difference is minus 1313 kilojoules per mole. And since this is 0, if you then go down minus 1313 kilojoules per mole, you get to negative 1313 kilojoules per mole. Okay. And we have done just n equals 1 so far. Now let's do n equals 3. And final equals 3. We'll do that in red. This time it's going to be 1 over 3 squared, or 1/9 of this number. So let's go ahead and plug that in. 2.18 minus exponent 18 minus. Still got the 1 squared, which is still 1, and we don't have to do the math there. Then, so 1 over 3 squared, or 1 over 9, so just divide it by 9. I get 2.42 times 10 to the minus 19 joules per electron. Well, joules is the calculation there. Then it's for 1 electron moving, so we put in the joules per electron. Run through this process again, divide by 1,000 times Avogadro's number, and I'll go back to, oh, don't forget your minus sign. 2.42 minus exponent 19 minus, divided by 1,000 times 6.022 exponent 23rd, minus 146, let's say, 146 kilojoules per mole. And let me slide over here. Again, this is for the process of starting at n equals infinity and going down 146. And that is the n equals 3 line. And that will be minus 146 kilojoules per mole. And I've gone down about I think a tenth or so, since it's about a tenth of the distance down here. And if we were to go, let's see, so that covers 3. And so our ladder looks like this. Here are the 3 rungs. 0, 3, n equals 1 is way down here. You could use the calculation here for 1 and 3, and you would get the difference between 1 and 3 here. So about, I don't know, about 1100 plus or minus kilojoules per mole difference there. The equation is totally useful. What you would see, though, is that the spacing of the rungs in terms of energy depends on 1 over the square of the number. So each rung on the ladder gets squared closer and closer to each other each time. If we were to try and approximate the n equals 2 value in here, it would be somewhere there. So the difference between 1 and 2, n equals 1 and n equals 2 is a big jump, and then each successive jump gets smaller and smaller until we get to n equals infinity. Calculate the energy difference between n equals 1 and n equals 2 energy levels for a helium ion. Let's go ahead and do it. We have our first part of the equation, helium plus, that is a 1 electron system, so we can use this equation. However, Z is going to be 2, and we end up with Z squared or 2 squared. So between 1 and 2 energy levels for a helium ion. So we're going to assume that let's go from Ni equals 1 and final equals 2. So 2 squared minus 1 over 1 squared. Plugging this in, let's start with this portion over here first. So 2 squared inverse minus 1 squared inverse. I get minus 0.75 times 2 squared times 2.18 negative exponent 18 minus. See if that worked out. Yes. It is positive because my 2 negative signs cancel out. I get 6.54 times 10 to the minus 18 joules as the amount of energy between those 2 energy levels for a helium plus ion. Now, this equation, one of my favorites by the way, hint hint, is calculating the energy for shifting an electron from one energy level to another. So we're going to use, even though this equation only gives units of joules, it is for the movement of one electron. So per 1 electron moved, we will add the units of joules per electron here and you'll see this in future examples. Now, this is also true that we can calculate and have calculated the energy of a photon of light based on this energy. And when we do that, we will add the units per photon. And so this energy is associated with a specific thing happening. It is for the movement of an electron in a helium atom, here's the nucleus, going from n equals 1 to n equals 2. And that process, since it's a positive energy, will absorb a photon with a specific wavelength. So this equation can give you any set of the 3 units since it's associated with this process. Now, this one's going to be a companion problem. It's a very similar problem, except from 2 to 3, and we'll do n equals ni equals 2 and nf equals 3. I will leave it for you to solve. Great practice, by the way. However, I will tell you at least one thing about it, and that is as you go from 2 to 3, the energy difference will be smaller, or the energy change, or the energy will be smaller than for ni equals 1 to n final equals 2. And that's because as you go from the nucleus outwards, the energy levels are getting closer and closer together as you move away from the nucleus. And that's represented from that equation where energy levels are in the denominator, and in fact the squared is in the denominator. So just something, a nice trend to point out.